124 light-years away, floating in the cosmic dark, a planet 8 times more massive than Earth just gave us the strongest signal, yet that we are not alone. James Webb Space Telescope has detected molecules in its atmosphere that on our world are only created by living things. We're talking about dimethyl sulfide, methane patterns, and water signatures that match the chemistry of life itself. This isn't speculation anymore. Scientists are calculating a 99.7% probability that biological processes are happening right now on this distant ocean world. Subscribe to witness history unfold as we dive into the most important discovery in human history. Prepare yourselves. We begin. The computer screen flickered with rainbow lines that made astronomer Niku Meduzan lean forward and whisper a single word. Impossible. What he was seeing should not exist. The spectral data streaming back from James Webb Space Telescope showed chemical signatures from a planet so far away that its light had been traveling since before humans invented writing. Yet there, glowing in infrared wavelengths, were molecules that spelled out a message written in the language of life itself. Picture trying to identify a single drop of perfume in a swimming pool from 3 meters away. That's essentially what James Webb had just accomplished. Detecting trace amounts of specific molecules in the atmosphere of planet K218 across 124 light-years of empty space. Each wavelength of light told a story about what gases were floating in that alien sky, and the story they told was breathtaking. The data revealed something called dimethyl sulfide floating in those distant clouds. On Earth, this molecule has one source, and one source only: living organisms. Marine phytoplankton pump it into our atmosphere every single day. It's the chemical signature of biological activity, as unmistakable as a fingerprint. But this wasn't the only surprise hiding in the rainbow spectrum. Methane and carbon dioxide appeared in ratios that matched the atmospheric chemistry of early Earth. Back when our planet was young and teeming with primitive life, water vapor signatures danced through the data like liquid evidence of vast oceans beneath hydrogen clouds. Meduzan called his colleague at Cambridge University. "You need to see this immediately," he said, his voice barely containing the excitement that comes with discovering something that changes everything. "We're looking at atmospheric chemistry that defies every natural explanation except one." The numbers were staggering. The probability calculations kept pointing to the same conclusion. Biological processes were actively occurring on this world right now, this very moment. As you read these words, the atmosphere contained exactly the cocktail of gases you would expect from a thriving oceanic ecosystem. For decades, scientists had searched the cosmos for signs of life beyond Earth. They had found frozen water on Mars, organic compounds on asteroids, and potentially habitable worlds orbiting distant stars. But they had never found anything like this. Active, ongoing biological signatures streaming through space like a cosmic calling card. The Discovery team ran the analysis 17 different ways. Every mathematical model, every chemical simulation, every atmospheric physics calculation pointed to the same stunning conclusion. Something alive was breathing, eating, reproducing, and dying in the skies of planet K218. What made this discovery even more remarkable was that it almost didn't happen. James Webb had been pointed at this particular world to study its basic atmospheric composition, not to search for life. The biosignatures appeared as an unexpected bonus, a cosmic gift wrapped in starlight and delivered across the vast emptiness of space. Yet, this was only the beginning of the story that would rewrite every textbook on astrobiology. Within hours of the discovery announcement, every major observatory on Earth was scrambling to point their instruments toward the constellation Leo. 218 bits had transformed from an obscure catalog entry into the most important celestial object in human history. Astronomers who had spent their careers studying distant galaxies suddenly found themselves canceling observations to focus on this single point of light floating in the cosmic dark. Conference calls erupted across continents as scientific teams coordinated the largest collaborative observation campaign ever attempted. What made this world so special wasn't just the potential for life. It was the perfect combination of factors that made detection possible. Think of it like finding a needle in a haystack, except the haystack is the size of the entire universe, and the needle is glowing with exactly the right color of light. 218 bits orbits its star in a way that creates what astronomers call a transit. Every 73 Earth days, the planet passes directly between its star and our telescopes, blocking a tiny fraction of starlight. During these cosmic eclipses, some starlight filters through the planet's atmosphere before reaching our instruments. That filtered light carries the chemical fingerprints of whatever gases float in those alien skies. The discovery triggered a gold rush mentality in the astronomical community. Research teams that had been working on completely different projects suddenly pivoted their entire focus to this single world. Graduate students found themselves reassigned to analyze atmospheric data instead of studying black holes or galaxy formation. Postdoctoral researchers who had never worked on exoplanets before were crash coursing in atmospheric chemistry. Space agencies began fast-tracking missions that had been sitting in proposal stages for years. The European Space Agency dusted off plans for next-generation space telescopes specifically designed to study potentially habitable worlds. Private companies started calculating the cost of sending robotic probes on 100-year journeys to actually visit this distant ocean. But the most dramatic change happened in the funding world. Astrobiology programs that had struggled for decades to secure adequate resources suddenly found themselves drowning in research grants. Universities competed to hire specialists in atmospheric spectroscopy and exoplanetary science. The search for extraterrestrial life, once considered a fringe scientific pursuit, became the hottest field in astronomy overnight. Social media exploded with speculation and excitement. The hashtag K28b trended globally as millions of people shared their thoughts about humanity's potential cosmic neighbors. Science museums prepared new exhibits almost instantaneously. Planetarium shows were rewritten to feature this remarkable world. Religious leaders grappled with theological implications, while philosophers debated what the discovery meant for human uniqueness in the universe. Science fiction writers found themselves struggling to imagine scenarios more exciting than reality itself. The planet had become more than just a scientific curiosity. It represented the answer to one of humanity's oldest questions: are we alone? For the first time in human history, the data was pointing toward a resounding no. Yet beneath all the excitement lay a sobering reality that few people were discussing publicly. Dimethyl sulfide smells like rotting cabbage mixed with ocean water. But it might just be the most important molecule in the universe. This simple chemical compound consists of just 5 atoms. One sulfur surrounded by 2 carbon atoms, each bonded to 3 hydrogen atoms. On Earth, every single molecule of dimethyl sulfide in our atmosphere comes from the same source, living organisms. There is no known geological process, no chemical reaction, no natural phenomenon that can create this molecule without biology. Picture the most remote ocean on our planet, thousands of miles from any land. Even there, microscopic phytoplankton are constantly pumping dimethyl sulfide into the atmosphere as they go about their daily business of photosynthesis and reproduction. These tiny marine organisms produce approximately 20 million tons of this chemical every single year, making it the primary source of sulfur in Earth's air. The molecule plays a crucial role in cloud formation over our oceans. When dimethyl sulfide rises into the atmosphere, it undergoes chemical reactions that create particles around which water vapor can condense. These particles become the seeds of clouds that help regulate our planet's temperature and weather patterns. In essence, microscopic life forms are actively participating in Earth's climate system. Scientists have searched extensively for non-biological ways to produce dimethyl sulfide. They have subjected various minerals to extreme temperatures and pressures. They have simulated lightning strikes, volcanic eruptions, and asteroid impacts. They have tested every conceivable chemical reaction that might occur naturally on a rocky planet. The result has always been the same. No dimethyl sulfide without life. This makes the molecule what scientists call a biosignature, a chemical that reliably indicates biological activity. Unlike other potential signs of life that could have geological explanations, dimethyl sulfide is unambiguous. Its presence in any planetary atmosphere would be like finding a note written in a language that only living things can speak. The detection of this molecule in the atmosphere of K-28b sent shockwaves through the scientific community precisely because of its biological exclusivity. When James Webb Space Telescope identified the spectral signature of dimethyl sulfide in those distant clouds, it was essentially detecting the waste products of alien metabolism floating in space. But here's where the discovery becomes even more remarkable. The concentration of dimethyl sulfide detected around K218 bits is actually higher than what we typically measure in Earth's atmosphere. This suggests that whatever organisms are producing it on that distant world are either more abundant or more active than the phytoplankton in our own oceans. The implications stagger the imagination. We're not just looking at evidence of life. We're potentially looking at evidence of thriving, abundant life. An entire ecosystem of microscopic organisms breathing, eating, reproducing, and releasing their chemical waste products into an alien sky 124 light-years away. The molecule had revealed its secrets across the vast emptiness of space, carrying a message that took 124 years to reach our telescopes. But the message it delivered was worth the wait. Something was alive out there, and it was talking to us in the universal language of chemistry. Mathematics doesn't lie, and the numbers streaming back from K218, we were telling an incredible story. Scientists don't just look at atmospheric data and guess whether life might exist. They use sophisticated mathematical models that calculate probabilities based on thousands of different variables. Think of it like a cosmic crime scene investigation where every molecule is a piece of evidence that either supports or contradicts the hypothesis of biological activity. The calculation begins with something called the chemical disequilibrium principle. On a lifeless world, atmospheric chemistry tends toward a state of balance where all possible chemical reactions have reached completion. Oxygen reacts with methane until one or both are consumed. Carbon dioxide dissolves into any available water. Over millions of years, the atmosphere settles into a stable, predictable pattern. Life throws this balance completely out of whack. Living organisms constantly pump gases into the atmosphere that shouldn't coexist under normal chemical conditions. They produce oxygen and methane simultaneously. Even though these gases react with each other, they maintain carbon dioxide levels that differ dramatically from what geology alone would predict. When scientists analyze an exoplanet's atmosphere, they first calculate what the chemistry should look like if only geological processes were involved. Then they compare this baseline to the actual observations. The bigger the difference between predicted and observed chemistry, the higher the probability that biological processes are interfering with natural atmospheric evolution. The atmosphere of 218 bits showed chemical signatures that were wildly out of equilibrium. Methane coexisted with water vapor in concentrations that defied purely geological explanations. Carbon dioxide levels fluctuated in patterns that suggested active removal and replenishment. The presence of dimethyl sulfide added another layer of chemical impossibility to the mix. Researchers ran computer simulations, modeling every conceivable, non-biological process that might explain the observations. They tested scenarios involving volcanic activity, lightning strikes, meteor impacts, and exotic atmospheric chemistry. They pushed the models to their absolute limits, looking for any possible way that geology alone could account for what James Webb was detecting. The results were definitive. The probability that purely geological processes could produce the observed atmospheric chemistry was less than 0.3%. This meant there was a 99.7% chance that biological activity was responsible for the chemical signatures. But the calculation didn't stop there. Scientists also had to consider the possibility of instrumental error or misinterpretation of the data. They reanalyzed the spectral information using multiple independent methods. They compared results from different instruments on James Webb Space Telescope. They invited rival research teams to examine the data and attempt to find alternative explanations. Every analysis confirmed the same conclusion. The chemical evidence for life was overwhelming, unprecedented, and mathematically undeniable. The probability calculations had crossed the threshold that scientists use to claim a discovery. The same statistical standard applied to everything from particle physics to climate science. These weren't wild speculations or hopeful interpretations. They were cold, hard numbers generated by rigorous mathematical analysis of empirical observations. The universe had presented humanity with an equation, and the solution was life. Yet, probability isn't certainty, and the most important questions still lay ahead in the data that remain to be analyzed. Sometimes, the universe aligns in ways that seem almost too perfect to be accidental. And 218 bits represents one of those cosmic coincidences. This world sits in what astronomers call the Goldilocks zone. It's certainly not too hot, not too cold, but just right for liquid water to exist on its surface. But location alone doesn't guarantee habitability. Hundreds of other exoplanets orbit within their stars' habitable zones, yet most of them are hostile to life as we know it.